In this video, I'm going to go over iperf 2.0.14's network power metric. It's a bit of a misnomer, but it's still useful. It was taken from the paper by Jaffe, written in 1979 about, sort of how to optimize TCP and how difficult or impossible that really is because of not having sufficient information to do a full optimization. But anyways, what's relevant here is the metric that he took, which was the network power. It's called network power. It's not like power in physics or anything, but it is an over time thing. So it's a bit of a misnomer. It was defined by Jaffe in 1979. It's basically something good over something bad, and that, and if you watch a value, it means the larger it gets, the better, and the smaller it gets, the worse. It's worse, and then you can take derivatives of it and things like that for regression signals. You can use one metric instead of multiple metrics to sort of monitor maybe a network device's performance, both in just not in resource consumption as well as in sort of typical performance of throughput. So anyways, good over bad, network power. It's in both UDP and TCP. You'll see it with the header here, and then it's a final number. The number, like I said, isn't very useful from a unit perspective. It doesn't really mean much, but it's good from a regression signal perspective. So, and it's good for a comparison perspective. You could have the same throughput, but a different power number, and you want the higher power number for that throughput. So, if you're doing scripts or doing regressions, you want to use that. So, anyways, it's supported in both iperf 3. It's supported in 2.014 in both TCP and UDP. So let's see how that works. Let's do TCP first. It's basic again. It's sort of the good, which is throughput, over the bad, which is how long or the speed, so to speak, to get that throughput. So you'll start the iperf server up, and if we do I don't want to do it necessarily isochronous. Let's just do a regular TCP streams. You have to use trip times for this, so that does require clock synchronization, because to measure in TCP, what you're measuring is the write to the read time. So I start the write on one computer, and it finishes the writes, and the other computer starts to read when it gets across the pipe and finishes the reads, and that's the time it takes to get a write to read, and that's what's being used to help produce network power. So if you need the trip times option, so you'll see the trip times, and then you see the last number here is network power, and so you see 394. It's just a number, so that's sort of interesting. Let me put the -e here to see something, give a better number. Okay, so the -e is showing you this is actually, you get it on both sides. You get the network power from an end-to-end perspective on the server, and then from a stack perspective, you're getting it, which is basically the RTT divided, in this number. So it's saying for that amount of time and memory, as the RTT grows, the memory grows, you're getting this throughput, this network power. So for an example, if I use the -z and use BBR instead of cubic, which is a default on this computer for the TCP congestion control algorithm, you should see an improvement there, and so yeah, you see a significant improvement, 3 times higher number here, and all because you drop the RTT and you get the same throughput. So if you're a network device manufacturer and you're trying to say, hey, how do I get good performance, and you want to minimize memory consumption and what time, maybe you want to look at more than throughput. You want to look at sort of the network power, how well are you doing. That's less for semiconductor companies. That's less transistors needed, less energy needed to run memory and all that kind of stuff. So network power is a nice metric to use. Like I said, the units don't have a lot of meaning, but once you sort of get used, you're looking for sort of regressions, but the number is of interest and it's useful.